In this video, we're going to talk about some trends that exist in the periodic table that correspond to where the electrons are in our current model of the atom. So this is interesting because quantum theory, which came along much later than the structure of the periodic table, was confirmed by how the periodic table was laid out. The periodic table was laid out based on chemical properties of the elements, and that structure, where the rows and columns are, that existed before anybody had any idea about these quantum numbers and shells and subshells and all that stuff. But it was a good confirmation that probably something in this quantum model of the atom appeared to be right because it did match up with and explain some of the structure of the periodic table. Much of what we're going to be discussing in this lecture has to do with this law, Coulomb's law, which we've seen before, but it's just to restate it here. It's that the electrostatic force, the attraction or repulsion between any two charged objects, is equal to a constant number, that's the K, we don't have to know what that number is for our purposes, times the charge on one object, K1, times the charge on the second object, Q2, divided by the square of the distance between the two objects. Now, if our two charged objects are the nucleus and an electron in the atom, Q1 could be thought of as Z, which is just the electron charge times the number of protons, because electrons and protons have the same charge. And then Q2 is the charge on an electron. It's just E. And then the square of the distance between them, well, in the quantum mechanical model of the atom, we don't have orbits like my simple model here is showing. Instead, we have a probability of finding the electron in any space. But you can think about an average probability zone as being a radius of an orbit, just to help understand this a little bit better. If you're thinking about the electron as a particle, it's going to spend most of its time at some average distance from the nucleus. So let's think about that as the radius sort of an orbit, even though that's not really how electrons function, but it's a good enough model to explain what we're doing here. So that means Coulomb's law for an electron takes the form of the electrostatic force is proportional to the number of protons times the electron charge divided by r squared. And the only things that are going to change from atom to atom are the radius, how big and small the shells are that the electron is in, and the charge in the nucleus, Z. The charge in an electron isn't going to change, and we just took out the constant because we don't really have to know any real numbers here. We just have to be able to make comparisons from atom to atom. PES confirms this idea because if you think about, we'll just look at a few examples here. Think about nitrogen with its 1s subshell closest to the nucleus, small radius, that means the denominator is small, so that means that would tend to make the electrostatic attraction big, and the 2s with a larger radius, that would mean a bigger number in the denominator, which would tend to make a smaller ionization energy, and the 2p on average even a little bit farther away from the nucleus, so making the denominator even bigger, which makes the electrostatic force even smaller, so the ionization energy that's required to overcome that force is even smaller. And then with oxygen, as we scooch over, why we're doing that is because in the numerator of Coulomb's law, the Z just got bigger, but the radius stayed approximately the same. Not completely, but they're both in the same shell. The outside electrons are in the 2 shell, in fact in the 2p subshell. So what really changed there was the Z in the numerator. However, because of that increase in attraction for the outside electrons, the ones that are in the 2p shell, in oxygen compared with nitrogen, the radius of the atom actually does get a little bit smaller because now the attraction for the outside electrons is a little bit bigger because of that bigger Z. So the radius does shrink a tiny bit. So that means as we increase in atomic number going across the period, so in this case from nitrogen to oxygen, and then if we went further to fluorine, that means the size of the atom is shrinking a little bit as we go across a row. So you might ask yourself, why wouldn't they just keep getting smaller and smaller and smaller. In fact, they don't. This is an atomic radius versus atomic number graph. And we can see that there isn't just a gradual decrease in atomic radius, even though the Z is continuing to get bigger and bigger and bigger. Instead, what we see is there are some periodic trends. At first, we have the atoms getting bigger until we get to lithium. And then that's the beginning of a row. If you look at its position in the periodic table, that's number 3. It's in the very leftmost column. And then the radii get smaller, and that's because the Z's are getting bigger. So the next one after lithium will be beryllium, then boron, carbon, nitrogen, oxygen, fluorine. Those continue to get smaller and smaller and smaller, and finally we get neon at the very end. And then when we get to the next row, which is sodium, the radius jumps up again. And then it gets smaller, 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 until we get to the end of the row. So there's 8 points there: sodium, and then magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and then finally argon, and then potassium. Start of a row, start of a new downward trend, but that downward trend starts at a much higher value. And then you can predict the next is going to be rubidium. It's the next one down in that first column, then cesium. And so we see this trend in the periodic table that as we go from left to right on the periodic table in a particular period or row, we see the size of the atom in general shrinking. Now, it's not a complete 100% certainty that the next atom is always going to be smaller. You can see there's some anomalies in there, some variations to that theme, but in general, as you go from left to right in a periodic table, especially for the main group elements, the radii get smaller and smaller. The reason for this is because there are some shielding electrons. The electrons that are in the inner shells of an atom, in a sense, absorb some of the charge of the nucleus and shield those outside electrons from that charge. And so we can think about an effective nuclear charge, which is Z effective in this equation up in the upper right-hand corner, as being the actual Z, the actual number of protons, the atomic number, minus the number of shielding electrons. The number of shielding electrons are the electrons that are in the shells that are lower than the highest shell. So that number, S, would be the atomic number of the noble gas that came before it. So for example, the number of shielding electrons for these first column elements that we have in this chart that are labeled would be, so let's take sodium as an example. Sodium has 11 protons, that's Z. The noble gas that comes just before sodium is neon, which has an atomic number of 10. That means there are 10 shielding electrons. That gives us an effective nuclear charge of 1. And if we go to potassium, well, this is 19, that's Z, but argon has 18 protons, which means the neutral atom is going to have 18 shielding electrons for that potassium. So 19 minus 18 is 1. So the effective nuclear charge for everything in this column is 1. And then if we move over to the next column, it's going to be 2. Like with magnesium, for example, moving over 1 from sodium, it's going to be 12 minus 10, which is going to give you 2. And then if we go over 1 more to aluminum, that's going to be 13 minus 10, which is going to be 3. So the effective nuclear charge keeps getting bigger and bigger because Z is getting larger, but the number of shielding electrons is staying the same. So those outside electrons experience a bigger pull, and that pulls them in a little bit tighter to the nucleus and makes the radius get smaller. There's a second trend, and that is that as we go down the group or down the column, we see the atom get larger. And the reason for this is because, as we have seen, the effective nuclear charge for everything in this column is 1. But what's happening is the electrons are in a shell that's a bigger shell. So the outer shell for lithium is shell 2. The outer shell for sodium is shell 3. The outer shell for potassium is shell 4. That's just the row number. So the atoms are just getting larger for that reason as we go down a group in the periodic table. Let's do some comparisons with two actual elements. Let's look at sodium. Sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. Magnesium is 1s2, 2s2, 2p6, 3s2. So the effective nuclear charge is just the atomic number. For sodium, that's 1, 11. For magnesium, it's 12. The number of shielding electrons, those are the electrons that aren't in the highest shell. So in that case, that's all the 1s and 2s, and that's 10, which is the atomic number of the previous noble gas. It's the same thing for magnesium. All the 1s and 2s add up to 10 electrons. So the number of shielding electrons in both cases is 10. So the effective nuclear charge for sodium is 1, 11 minus 10, and for magnesium it's 2. So for magnesium, the numerator in that Coulomb's law comparison equation that we can use is bigger than for sodium, which means the outside electrons, the electrons in the 3 shell, for magnesium are going to be pulled in a little bit tighter than sodium's because the effective nuclear charge is a little bit bigger. So we should see magnesium have a smaller atomic radius than sodium. And when we put the numbers up here, we see in fact that that is the case. The atomic radius of sodium is larger than the atomic radius of magnesium. Let's make another comparison. Let's duplicate the 1s2, 2s2, 2p6, 3s1 electron configuration that we had for sodium. For potassium, which is in the 4th period, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. If we look at the shielding electrons, we've already done this for sodium. Those are the 1s and the 2s. There's 10 shielding electrons. Sodium's atomic number is 11. Shielding electrons being 10, that leaves us with an effective nuclear charge of 1, as we've seen before. For potassium, the outer shell is 4, so that means the shielding electrons are everything that aren't in shell 4. And that's going to be 6 plus 2 is 8, plus 2 is 10, plus 6 is 16, plus 2 is 18. So there's 18 shielding electrons. The atomic number of potassium is 19, so the effective nuclear charge here is also 1. So that means that the numerator of that Coulomb's law comparison equation is the same for both of these. However, the outermost electrons are in the 4th shell for potassium compared with the 3rd shell for sodium. And that means that potassium has to be larger because by definition shell 4 is bigger than shell 3. And so those electrons are just farther away and experience the same effective pull towards the nucleus. And the numbers show that here. 186 was our atomic radius for sodium. 227 is the atomic radius for potassium. There is a trend in ionization energy as well. Again, going back to our atom, thinking about the energy it takes to remove an electron completely from the atom, that's the ionization energy. And just a reminder that that force, electrostatic force, that's going to be proportional to the effective nuclear charge times the charge on an electron divided by the square of the average radius of the shell that that electron is in. Here are the trends that we see in ionization energy. Hydrogen, number 1, is fairly low. Number 2 is helium, and it jumps up quite a bit. Then we see a drop down to lithium, and then we go across the 2nd period, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then we get a high at neon, and then it drops down again. And then we go through the 3rd period, through all of those elements, and we see argon, the next noble gas, being a high spike. And then krypton. Now that's a longer stretch because we have 3D electrons in there. And then finally we get xenon. So the high spikes in ionization energy occur at the noble gases. And this explains why they don't react very well, because it's hard to take electrons out of them and turn them into ions because the ionization energy is very high. On the other hand, it's fairly easy to take electrons away from, say, lithium or sodium or potassium those group 1s because their ionization energy is very low, so it doesn't take much energy to overcome the force that's holding the electrons to the nucleus. Once again, this is explainable by that Coulomb attraction. As we go from left to right across a period, what's happening is the effective nuclear charge is increasing while the radius is staying pretty much the same, but actually shrinking a little bit, because we've seen in our last few slides that as we go across a period, the radius is shrinking a bit. So both the numerator and the denominator are dictating that it's going to be harder as you go from left to right in a group to remove the electrons, which means the ionization energy is going to rise. And then when we start a new row, the effective nuclear charge drops back down to 1, and then we build back up again until we get the highest ionization energy in that row, which is at the very right-hand side for the noble gas. So that's the trend that we're seeing there. As we go from left to right across each period, we are going to see increased ionization energy. And just a reminder that it's because the effective nuclear charge increases across a period because the Z's are getting bigger and the S's are staying the same, and the radius decreases a little bit because of that increased nuclear charge. A second trend that we see is that if you look at the peaks at all the noble gases, or if you take the halogens, the fluorine, chlorine, bromine, iodine, or pick any group that you want to, as you go down that group, the ionization energy decreases. Once again, this is explained by that Coulombic attraction. Here, if you pick a group, that's a column on the periodic table, the effective nuclear charge is going to be the same for every one of them. But as the atoms get larger and larger, because the outside electrons are in bigger shells, that means the denominator of that Coulombic equation, the radius, is going to be bigger, which means the electrostatic force is going to be smaller, and that's going to make it easier to pull those electrons away. So the rationale for this is the effective nuclear charge stays the same down a group, but the radius is going to increase, which makes the ionization energy go down. What we were looking at there was the effective nuclear charge for the first ionization, when you take that first electron out. If we look at ionization energies after the ion has become a 1+ ion, in other words, you've removed one electron, the effective nuclear charge is going to stay the same because you haven't removed any shielding electrons. You've only removed outer shell electrons. And it's the same atom, so the Z is still the same. And the radius is pretty much still the same because the remaining outer shell electrons are still in the same outer shell. But what does happen is, now after having removed one of the electrons from that outer shell, there's less repulsion between the electrons. Remember, they're all negatively charged, so they repel each other just a little bit, and that makes them get a little bit farther away from each other. And that makes the radius a little bit larger than it otherwise would be. So let's say you had 3 outside shell electrons, like in this little simple case, and you take one of them out of there. That means now you have only 2 electrons repelling each other, and so they can draw in a little bit closer to the nucleus because they don't have to stay away from each other, kind of. So that's going to shrink the radius a little bit, and if the radius shrinks, then that means the denominator got smaller in the Coulomb's law equation, and so that means the ionization energy is going to go up a little bit. So as you remove subsequent electrons from the outer shell after the first ionization, the ionization energy just keeps going up and up and up and up. Example, magnesium. The first ionization, you're taking a magnesium atom and you're removing 1 electron to make a magnesium 1+ ion. The ionization energy for this is 738 kilojoules for a mole of ions. If you do the second ionization, where you take that Mg+ and take another electron away to make it Mg2+, the ionization energy for that is larger. It's 1,450 kilojoules per mole, about twice as big. When we go to take the third electron away and make that Mg2 plus into an Mg3 plus, the ionization energy doesn't double. It goes way, way up. Why would that be? Let's take a look at the electron configuration notation. Magnesium is 1s2, 2s2, 2p6, 3s2. When you take one electron away, you're taking it from the outer shell, so that means it's going to be 1s2, 2s2, 2p6, 3s1. Okay, take that and remove the second electron. Now you're taking a second electron from that 3s subshell. So it goes from 1s2, 2s2, 2p6, 3s1 to just 1s2, 2s2, 2p6. What happens when we take the third electron away is now we're reaching down into an inner shell which is much closer to the nucleus and therefore much more strongly held by that nucleus, by the Coulomb's law equation. And we have to remove one of the 6 2p electrons to make that third ionization. That takes quite a bit more energy. And in fact, magnesium typically is not going to make a 3 plus electron because of that reason. Here's a three-dimensional chart that kind of lays this out for us. Along this edge, what we have are the groups: sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon for the third period. And along this axis, we have the ionization energies. And you can see for column 1, sodium, the first ionization energy is small. The second ionization energy is much, much larger. Sodium is typically only going to make a 1 plus electron because after removing that first electron, it's much harder to remove the second one. Why would that be? Because sodium ends in 3s1, its electron configuration. So if you take that 3s1 electron away, now you're removing a 2p electron, which is way closer to the nucleus. Look at magnesium, we just looked at this one. The first ionization energy is small, the second ionization energy is bigger, the third ionization is way bigger. And so magnesium is going to make a 2 plus ion. Aluminum, first one smaller than the second smaller than the third, but there's sort of a linear trend here. But the fourth ionization energy is way, way bigger. So aluminum makes a 3 plus ion. It doesn't make a 4 plus ion. So we see that trend in group number and ionization. Group 1s make 1 pluses. Group 2s make 2 plus. Group 3s make 3 plus. And so on. Group 4s would make 4 plus, but they typically don't ionize that much because 4 electrons turns out to be a lot to remove. And so for the rest of those elements, we're going to find out that they ionize in a different way. Another change that happens in atoms is when electrons could be added to an atom. And when that happens, energy is typically released when the first electron is added to an atom. And that's because the electron is attracted to the nucleus, and so an electron that's outside of the atom, when it's allowed to become closer to the nucleus that it's attracted to, the energy stored in the fact that they were held apart from each other is now released. And that amount of energy that gets released is called the electron affinity. The attraction for incoming electrons is going to be greatest when these conditions exist. The first thing is there's a high Z. In other words, the nucleus is large, has a lot of charge, not large necessarily, but has a large charge, and that's attractive to an electron. The bigger the positive charge in the nucleus, the more attractive the electron is. And when they will end up being close to the nucleus, which means the radius of the shell that they're going to end up in is a small radius. So that means small atoms, which means small shells. So that means that as you get towards the right-hand side where the effective nuclear charges are bigger, and towards the top where the shells are smaller, that's where you're typically going to see your largest attraction for incoming electrons. And if you look at a chart of this, another three-dimensional chart, you can see that up in the upper right-hand corner where fluorine and chlorine are, the electron affinities are very high, and then as you go back towards the left and towards the bottom of the table, down towards rubidium and cesium and strontium and barium, those things are very low electron affinities. So elements that are on the right-hand side tend to attract electrons to themselves and become negatively charged ions much more readily than things that are on the left-hand side of the periodic table. We've already seen that elements on the left-hand side are much more likely to lose electrons to become positively charged ions. So there's a pattern. Let's talk about the radii of ions, how large they are. Cations tend to be smaller than the neutral atom, and the reason for that is because the outer shell is unoccupied. So that means the outer shell, the new outer shell, is an inner shell from before. So here's an example. Magnesium, we've already seen, is 1s2, 2s2, 2p6, 3s2. But as an ion, that third shell is completely missing. And so magnesium 2 plus ion is going to be a smaller entity than a magnesium atom. And in fact, we see it's quite a bit smaller. Magnesium 2 plus ion is 72 picometers, which is kind of more typical of a period 2 element. And magnesium's radius as an atom, unionized, is 173 picometers. Anions, which are negatively charged ions, are larger than the neutral atom. And the reason for that is because the effective nuclear charge is still the same. So the draw for the outside electrons that's pulling them in is the same as it ever was. But now you've put one more electron in that outer shell. And because you've done that, that means there are more electrons in that outside shell to repel each other, and so that outside shell grows just a little bit. So here's sulfur, for example, 1s2, 2s2, 2p6, 3s2, 3p4. It can gain 2 electrons. Its outer shell has room for 2 more electrons. And when it does that, it's 1s2, 2s2, 2p6, 3s2, 3p6, which is basically the same thing as an argon, except with a smaller effective nuclear charge. So it's going to be even a little bit bigger than an argon. Here's the radius of both. Sulfur is 104 picometers. Sulfur 2 minus ion has grown to 184 picometers. Here's a little graphic that shows the sizes of ions compared with their original atoms. So on the left-hand side, where we find cations are more likely to form, we see that the cation, which is shown in red, is always smaller than the original atom. On the right-hand side, where the non-metals are, we see that anions are likely to form there, and the anions that are formed, which are shown by the blue half spheres, are significantly larger than the atoms that originally formed them.